So section 6.3 takes what we've done in section 6.1 and 6.2 to the next level. Now, if you do some reading in section 6.3, you'll notice it talks about something called the central limit theorem. The central limit theorem is critically important of our understanding of how to answer the next types of questions. Hopefully you've noticed in the previous sections we've been answering questions such as, if I randomly select one family or one person or one item, what's the probability that it's less than this or greater than this or between these two values? The central limit theorem does not deal with selecting one individual from a population. It deals with selecting a sample from a population. Okay, so let's read this example 1 to illustrate what that means. It says A.C. Nielsen reported that children between the ages of 2 and 5 watch an average of 25 hours of television per week. Assume the variable is normally distributed and the standard deviation is 3 hours. So key information, 25 is our mean, and the 3 is our standard deviation. It says this, not if one child, but if 20 children between the ages of 2 and 5 are randomly selected, find the probability that the mean number of hours they watch television will be greater than 26.3. So notice it does not say select one person and find that they watch on average less than or greater than some value. It's select 20 people. And then with those, or in this case children, in this case, select those 20 and then find the mean of those 20. And we're going to compare the mean of these 20 to the mean of the whole population. So we're taking 20 out of a full population of children between 2 and 5 and asking ourselves, what's the probability that the mean of those 20 is in this case greater than 26.3? So we do a lot of the same things, but we calculate one thing just a little differently. So we know our mean is 25, and we want to know what's the probability that the mean that we select, we're going to have a 26.3, and this in this case it's greater than. So the area that we're looking for is the area greater than the 26.3. So normally what we would do is we would calculate a z-score, where z equals x minus mu all over sigma. Here's the deal though. Because we're not dealing with a single, that's what the x represents, a single data point, we're dealing with a full sample and calculating the mean of that sample. So the z-score switches to this. Instead of z equals x minus mu, it's x bar. So what that means, whenever you put a bar over something in the reading that you've done, it means an average or a mean. So here's what it's essentially saying. This is the mean of the sample of 20. This is the mean of the population. So we know that the whole population of children between 2 and 5 watch an average of 25 hours a week. But if I take 20, are those going to average exactly 25? Well, no, it's going to be a little less, a little more. Because of just random variation in different samples. What if all of a sudden you sampled and the 20 you randomly selected didn't even have TVs at home? Or the 20 you selected, that's all they did was watch TV at home. You can see that the sample mean would deviate, it would vary compared to the overall population mean, where all types of children are included between the ages of 2 and 5. So we're not comparing a single value to the population, we're comparing a sample mean to the population mean. What this does though is it also switches our denominator. Instead of just sigma, we end up with sigma over the square root of n. The reason for this is this. The bigger our sample size gets, the closer we expect to get to the population average. If I select 2,000 kids rather than 20 kids, I expect the average of the 2,000 to be a lot closer potentially to the population than just the 20. When you have a small sample, there can be a lot of deviation from the full population of people. Okay? So we adjust that, and this accounts for it, divided by the square root of n. N is sample size. So in our case, it's the 20. So to calculate the z-score that we need to find area, we're going to go z is equal to the mean, that the mean is greater than 26.3. So we're assuming 26.3 minus the mean of the population, which is 25, divided by the standard deviation, which in this case is 3, divided by the square root of our sample size, which is 20. So we've got now some work to do in our calculator. I'm first going to do the denominator. I'm going to do 3 divided by the square root of 20. So this becomes, well, 26.3 minus 25 is 1.3. So it's 1.3 divided by 0.67. So that ends up giving us a z-score. So 1.3 divided by that value that I got gives us a z-score of 1.94 if I round to the nearest hundredth. 1.94. So that's the z-score that I'm going to be looking for, 1.94. So I go to my normal table, and 1.94, 1.9, but then the 4 column is this column here. So 1.9, 0, 1, 2, 3, and 4. So that's a 0.9738. 0.9738. So the area from here to the left, 0.9738. Because remember, the tables give you the area less than, not greater than, but less than. But I'm interested in the area greater than. So to finish this off, I'm going to have to do 1 minus 0.9738. So that ends up giving me 1 minus 0.9738, a 0.0262. So this area right here represents 2.62% of the population. So what that means is this. We can expect that if we take a sample of 20 kids, that the average number of hours that they watch TV, well, compared to the 26.3, there's only a 2.62% chance that the average of these 20 kids will be greater than or equal to the 26.3. So let's do this again to solidify it. In this case, looks like we have vehicle life. It says this: the average age of a registered vehicle registered in the United States is 8 years, or that's 96 months. Assume the standard deviation is 6 months. If a random sample of 36 vehicles is selected, find the probability that the mean of their ages is between 90 and 100 months. So we start with our normal curve here. We know our average here is 96, and we want to know from 90 up to 100. Now again, we're not selecting one individual car and finding the probability it's between 90 and 100. We're selecting a population, or rather a sample of 36 vehicles. So we need to find the z-scores for each of these values that we're supposed to be between, but we have to keep in mind how to calculate it based on 36. And these are not values, these are means, that the mean of these 36 vehicles' age is between 90 and 100 months. Again, not an individual car, but a group of 36 cars, and the average is between 90 and 100. So calculating the z-score, it's going to be z equals, remember, x bar, so the sample mean minus the population mean, all over the standard deviation, divided by the square root of n. So this first one, we'll call this z1 and this z2. z1 is going to equal 90 minus 96 all over standard deviation of 6, a 6 over the square root of 36. Well, I think we could do this one in our head. 90 minus 96 is negative 6 divided by the square root of 36 is 6. So 6 over 6 is 1. Okay, so that gives us a negative 6. A negative 6. So 90 minus 96 all over 6 minus 36. The next one is Z2. So let's do Z2 is equal to, in this case, it's going to be 100 minus 96 divided by 6 over the square root of 36. So 100 minus 96, that's going to be a 4 divided by, in this case, 6 over 36. The square root of 36 is 6, so 6 over 6 is 1. So that becomes a z-score of 4. Well, those are pretty big z-scores. What you're going to see is some interesting things happen with that. So I want to know the area under the curve to the left of each of these values, so that then I can do some subtraction to find the area between them. So I go back to my example here, or to my table here, and I need to look for the z-score of negative 6 and positive 4. What you'll notice here is that our z-scores only go down to negative 3.4. And you'll notice the more negative the z-score gets, the smaller this area gets. Notice it's all the way down to 0.0002. Okay? Here is what it says. For z values less than negative 3.49, use 0.0001. Okay, so the area under here, 0.0001. Now we've got to look for the z-score of 4. The same exact thing is going to end up happening. If we look over here, the z-scores only go up to 3.49. So a z-score any greater than that, what do we use? 0.9999. So the area south of, or to the left of here is 0.9999. So what is the area between those two? It's the 0.9999 minus 0.0001. Doing that math, you end up with 0.9998. That's all this area right here. So there's a 99.98% chance that if you randomly select 36 vehicles, that their average life or their average age is between 90 and 100 months old. So again, Chapter 6, Section 3 is about samples, not just an individual value, but a sample. And so we have to calculate the z-value, the z-score, a little bit differently to account for the fact that it's a sample that we're selecting and not just one individual that we're selecting.